This highway was not meant to fail. Designed for decades of service, it began showing distress far earlier than expected. Rutting, cracking, and surface deformation are not cosmetic defects, they are structural warnings. Every visible failure on the surface has a cause hidden below. Every crack visible on the surface tells a deeper engineering story below. Because highway failures do not occur suddenly, they develop layer by layer, load by load, until the pavement structure can no longer distribute traffic stresses safely. This is the hidden science behind highway failure, and understanding the real causes beneath the surface is the first step toward building roads that truly last. Pavement failure is rarely sudden. It develops progressively, month after month, load after load. What begins as microscopic damage evolves into visible distress and finally into functional collapse. By the time potholes appear, the pavement has already failed internally. Asphalt highway failures can be classified into structural, functional, material, construction, and drainage-related categories. Most failed roads do not suffer from a single cause. They fail due to a chain of engineering decisions made at different stages of the project lifecycle. Traffic estimation defines pavement life. When design traffic is underestimated, every axle load consumes more structural capacity than planned. Overloaded trucks accelerate damage exponentially, not linearly. No pavement can survive traffic it was never designed to carry. Pavement thickness is not a cost, it is a structural requirement. Insufficient thickness allows stress to penetrate into weak layers below. Once the subgrade begins to deform, surface failure becomes inevitable. Thin pavements fail quietly until they fail completely. Simplified design assumptions ignore real pavement behavior. Fatigue, cracking, and rutting do not appear in equations, they appear in the field. Pavements designed without mechanistic understanding often meet code requirements but fail in service. Design calculations assume ideal conditions. Reality delivers moisture, temperature variation, construction tolerances, and overloaded traffic. A design that cannot tolerate reality is not conservative, it is vulnerable. The subgrade carries the entire pavement system. Soft clay, expansive soil, or organic material reduces bearing capacity dramatically. Pavement layers above cannot compensate for a weak foundation. Subgrade failure always propagates upward. Inadequate soil investigation creates blind spots. Boreholes placed too far apart often miss weak zones. Pavement distress almost always appears where investigation was insufficient. Nature exploits every assumption engineers make. Compaction creates strength through density. Undercompacted subgrade settles under traffic, creating differential deformation. Once the pavement bends, cracking becomes unavoidable. Compaction errors cannot be corrected after construction. Aggregate gradation controls internal load transfer. Poorly graded mixes lack stone-to-stone contact. Under traffic, particles rearrange, leading to permanent deformation. Rutting begins inside the mix, not on the surface. Bitumen content defines flexibility and cohesion. Too little bitumen results in brittle cracking. Too much bitumen leads to instability and rutting. Asphalt mix design is a balance, not an approximation. Moisture breaks the bond between bitumen and aggregate. This process, known as stripping, reduces strength without visible warning. Pavement may appear intact while losing structural integrity internally. By the time stripping is visible, failure is advanced. Asphalt behavior changes with temperature. High temperatures reduce stiffness and promote rutting. Low temperatures increase brittleness and cracking. Ignoring climate is equivalent to ignoring loading. Pavement layers must act as a single structural unit. Without proper tack coat, layers slip under traffic. Slippage cracks indicate loss of composite action. This is a construction failure, not a material failure. Asphalt must be placed and compacted within a narrow temperature window. Cold asphalt cannot achieve required density. Poor temperature control permanently reduces pavement life. Air voids are the enemy of asphalt durability. Insufficient compaction leaves the pavement vulnerable to moisture and deformation. Density lost during construction is lost forever.
Roller passes insufficient. Air voids remain high. Early rutting develops.
Longitudinal and transverse joints are the weakest points in asphalt pavements. Poor joint construction allows water infiltration and crack initiation. Most early failures begin at joints. Quality control is a system, not a formality. Missing tests, ignored limits, and rushed approvals accelerate failure. Most failed pavements pass inspections until they fail in service. Surface drainage protects the pavement from water intrusion. Ponding increases moisture penetration and hydroplaning risk. Standing water is a design failure, not a maintenance issue. Trapped water beneath the pavement reduces effective strength. Pumping action removes fines, creating voids and collapse. Drainage is structural, not optional. Forensic engineering begins with observation. Distress patterns reveal failure mechanisms. Pavement cores expose internal damage invisible from the surface.
This alligator cracking correlates with the subsurface data on the tablet.
We should increase the sampling frequency in this quadrant.
Agreed. Document the distress levels here first.
Look at this fatigue cracking here. It extends further than the initial survey indicated.
The deflection data on the tablet confirms the structural weakness.
Asphalt highways rarely fail due to one mistake. They fail due to cumulative engineering compromises. Each shortcut shortens pavement life. Durable pavements demand realistic traffic estimation, strong foundations, controlled materials, disciplined construction, and effective drainage. Engineering rigor is always cheaper than rehabilitation. Pavement failure is not inevitable. It is predictable, preventable, and reversible through engineering responsibility. This is the lesson every failed road teaches.